Thank you, Nancy. And I think, well, the last question I think you can all answer, but with whom is, of course, also the patients. And what I want to do here in the next 35 minutes is to use the therapy development for Duchenne muscular dystrophy, where I work on, to showcase several things. Patient community involvement, but also the need for timely development of tools, and we'll get back to this. The importance of involving all stakeholders, so not just patients, but also other stakeholders. The importance of good communication, the importance of bilateral and trilateral education. I think this is something that already on the first day, several people said that they were hoping to learn from the people presenters, but also the presenters said that they were hoping to learn from the patients. And I think this is a good mindset to learn from everyone. And then finally, hopefully, we can all learn from the mistakes that we made in the Duchenne field. So a very brief introduction to Duchenne muscular dystrophy. It's an X-linked disease, which means that mainly boys are affected. Mothers can be carriers and pass the disease on to their sons, but generally they are not affected themselves because they have 2 X chromosomes. The disease is characterized by progressive loss of muscle tissue and muscle function. And you can see here, so this is a very small Duchenne patient. You can't really see anything yet, but already in this boy you can see that there's muscle problems, because what you see is that he rests with his arms on his leg. So he was asked to get up from the floor, and you can see that he needs this extra push on the leg, because the leg muscles don't have the strength to get up from the floor otherwise. You see the 2 boys that are still standing, you see that they have this weird pose, and that is because some muscles are lost earlier than others, and that means that what they need to do is to use the muscle that they have left to be able to still walk. Patients usually become wheelchair dependent around the age of 12. Then arm function also declines. You can see that this boy is using gravity to sling his arm up. You can see that this boy is, or young man, is still able to feed himself. But you can also see that he needs all hand and muscle function that he has still left. Patients usually need assisted ventilation around the age of 20, and the life expectancy is on average 30. But as with many diseases, because the patients are fragile and because the respiratory function is impaired anyway, if they have an infection, then pneumonia can become a killer, unfortunately. So there's also many patients that die earlier due to pneumonia and other respiratory complications. So I think it's clear this is a severe disease. There's currently no cure. There are therapies to treat the symptoms. So most patients are treated with corticosteroids, which slows down the disease progression. But chronic steroid use, of course, has a lot of side effects. So we're working on developing therapies, and many people around the world are working on developing therapies. And I think it's good to bear in mind the different steps. And those of you that went to UPathy, that went to the summer school, you will know these steps, but we'll reiterate. So the first step is fundamental research. You need to know what goes wrong, how this goes wrong, in order to know, okay, where can we intervene for our therapies. Then you need your proof of concept studies in model systems. We have an idea, does this really work? Then you need your preclinical study. So it seems to work, but now we need to plan a clinical trial. We need to know about the dose, the absorption, the route of delivery, etc. Then you can do your clinical trials, and then you need marketing authorization applications. So then the regulators will decide whether indeed this therapy is effective and the side effects are tolerable. And then you get, of course, the health insurance and the post-marketing studies. And it's important to understand all these different steps and what is needed. And I think that the problem that we had is that we usually go step by step by step and then only realize what we need for the next step when we reach the next step. So the Duchenne field The Duchenne field has patient organizations. So this is the logo of the Dutch Duchenne Parent Project, but there's parent projects here, there, and everywhere, and they're also united in the World Duchenne Organization. And what the parents have done, they have funded research already from an early stage. So the fundamental research that is needed at the start was mainly funded by the patient organizations. So what was done? So before the patient organizations' involvement, a gene was identified. So you may remember Ségolène's talk. So the dystrophin gene, the gene that's affected in Duchenne patients, that was found as one of the first genes. And why was that found as one of the first genes? It's very big, so that makes it easy to find. But then more research was needed. So okay, we know now that this gene is affected, but what protein does this gene encode? How does this protein work? How does it happen that if you don't have this protein, you get Duchenne? And a lot of this research was funded by patient organizations. So I think this is already a way that patients can be involved. So what we know that Duchenne patients cannot make a protein called dystrophin. And often people say that the dystrophin gene is the gene for the disease. Well, actually, the dystrophin gene is the gene that avoids that you get the disease. Because if you don't have dystrophin, you will get Duchenne. There's another disease, and we'll come back to that later, where the patients also have mutations in the dystrophin gene, but they make altered dystrophin. So what does dystrophin do? You can see a schematic depiction here. It binds to the cytoskeleton with the beginning part, and it binds to the extracellular matrix that covers each muscle fibers with the end. And in the middle you can see here it has these repetitive elements that more or less act like a string. So what it does, it acts as a shock absorber. So each time we use our muscle fibers, or the muscles and all the muscle fibers, this puts a lot of strain on the muscle fibers. And to avoid that the muscles are damaged, we have dystrophin, which has this shock absorbing function. So that means if you don't have dystrophin, every time you use your muscle, there will be damage. And of course this damage becomes chronic, and then eventually all the chronic damage will lead to loss of muscle tissue, replacement by fat and adipose tissue, and also loss of muscle function. So then you can say, well, if using the muscle is what causes the damage in patients, maybe they should not use their muscle. But we all know that if you don't use your muscle, you will also lose it. I mean, if you're in bed for a week, you will lose a lot of muscle tissue. So whatever these patients do, they will lose muscle tissue. But what's important to remember from this protein is that the two domains that are important for the function are at the beginning and the end. And in the middle, you have this repetitive domain. So a brief recap on how genes work, and apologies for those of you who know this already. So the genes encode the protein. And so each gene, we have 23,000 genes roughly, each of them encode one or more proteins. The genetic code of the protein is dispersed over the gene. And the regions that contain the genetic code are called exon. And this is so when people say whole exome sequencing, this is what is happening, is that they sequence all these exons, all the protein coding domains of all the genes, of all the proteins, they sequence them to see whether there's something wrong there. So if we go back to the dystrophin gene, then the dystrophin gene has 79 of these exons, but they're in the gene, the DNA. And the protein producing facility in the cell is located outside of the nucleus. So something needs to happen because the DNA cannot go out. The protein producing facility is quite big. It can't go into the nucleus. So what we need a temporary copy. So if a protein needs to be made, what happens is that a temporary copy called RNA or transcript is produced. So it's an exact copy. It has the exons, and it has also the parts in between that do not contain protein information. Now before this can be translated into protein, you need only the exons. You don't need these intervening things called introns. So during a process called splicing, all these introns are removed. The exons, the protein containing information, is all linked together. And then you end up with your messenger RNA that contains only the protein coding information. And that then is translated into protein. In our case, dystrophin, but this happens as we speak. This happens in all the cells of our body for all the proteins that we need. So mentioned this already, the dystrophin code contains 79 exons. And you can see here, they all fit together like puzzle pieces. And why is this important? This is important because Duchenne patients usually lack one or more of these exons. And if you, for instance, miss exon 48 to 50, what you can see is that 47 and 51 don't fit together. You can see that here again. And what happens is that this means that the reading frame is disrupted. So it becomes unreadable. So the genetic code is readable up till 47 and then becomes unreadable. So compare it to translating. So Marlene is quite good in French. So if you give her a French book, she can translate it into Dutch. But if then halfway suddenly the French becomes Chinese, she has to stop translating because she won't understand. Well, this is the same thing that happens here. So the genetic code is readable until 47, then becomes unreadable, so the translation stops. So what you get is a dystrophin protein that only has the beginning part. Well, and we know it has this bridge function. So the end part, the important domain at the end, is missing, so this protein is not functional. I already mentioned that there's another disease called Becker, where patients also have mutations. However, now patients have mutations that do not disrupt the genetic code. So you can see here, 48, 49, 50 and 51 are missing. So more is missing, but because 47 fits to 52, the genetic code is maintained. So now the reading frame is not disrupted and the translation can continue. 2 chapters have been ripped out of the book. So part of the story is missing, but for dystrophin this doesn't really matter because the important domains are there at the beginning and at the end of the protein. So what is missing is part of this repetitive domain in the middle, and well, it turns out that you can do without some of these domains because these patients, they have a muscular dystrophy, but the disease is a lot less severe than Duchenne. So the onset is later. Patients usually become wheelchair dependent 10 to 15 years after the onset of the first symptoms. Respiratory, so assisted ventilation is rare, and the life expectancy is near normal to normal. So compared to Duchenne, this is a lot better outcome. And the only difference here is that both have mutations in the dystrophin gene, only one disrupted the genetic code and the other does not. So for Duchenne, people have looked into gene therapy and cell therapy well, as soon as the disease was first discovered and described. But there's one problem, a big problem, and that is that we have a lot of muscle. So we have about 700 different muscles, and most of them are affected in Duchenne. We also we have 700 different muscles, but the muscle mass is also quite big. So about 30 to 40% of our body is muscle. So it means if you do gene therapy or cell therapy, you need to deliver a lot, which is challenging. Just imagine the cells, the amount of cells that you need. I mean, this is not like you need a small muscle biopsy. No, you would need literally an arm and a leg of someone else to get enough cells. Then you inject them, and then the next problem is that muscle is very inaccessible to large particles. So if you inject cells in the bloodstream, hardly any will go to the muscle. If you inject viral vectors into the bloodstream, some will go to muscle, but then, I mean, it's not enough that each muscle has maybe 1 or 2 of these viral particles. No, you need to have a lot. So that's why we started thinking, well, is there something else? Can we, not using smaller things, find a therapy for Duchenne patients anyway? And well, this is again based on the fact that we have the Duchenne patients where the genetic code is disrupted, and we have the Becker patients where the genetic code is maintained. And what we know is that many Duchenne patients in theory can make Becker-like protein. So we had the example of a patient who has a deletion of exons 48 to 50. And we saw already that 47 fits to 52. So if this patient could somehow, during the splicing process, so this is the process where all these exons are recognized and linked together before they can be translated, if we can manage to make the cell bypass exon 51 in this case, then the genetic code would be restored. And then this Duchenne patient would be able to make a Becker-like protein. Now, how can we do this? We can do this with very small modified pieces of RNA called AONs, antisense oligonucleotides. These specifically recognize this exon, hide it from the splicing machinery, and now the splicing machinery will just look for the next exon. This one is hidden, so it now connects 47 to 52. And that restores the genetic code, and now a Duchenne patient would be able to make a Becker-like protein, in theory. So then we had our idea, and we needed money to test whether this in fact worked. And of course we applied with the government funding, as you heard on day one, with government funding, with EU funding, and they all said, no, well, this is science fiction, this is way too complicated, we don't think this will work, we are not going to give you any money. So again, from the Dutch Duchenne patient organization, we received funding to do our initial tests. So this is in cultured cells derived from a patient. So I mean, this is a model system. So again, cultured cells from a patient lacking exon 48 to 50. Then we looked into the RNA, so this messenger RNA. And we looked before treatment and after treatment. And what you can see here is that after treatment you see something that is lower. Well, this is separated by size, so lower means shorter. And why is it shorter? Because, as we hoped what would happen, exon 51 is now gone. We also looked at dystrophin expression, so we stained cells, the cultured cells, for dystrophin. Before treatment, none of the cells made dystrophin. Of course, this was a patient. After treatment, about 75% of the cells started making dystrophin, stained in green. We also looked with another system where we just load protein and stain it afterwards. This is the healthy control, this is the patient before treatment, nothing happens after 4 hours, nothing after 8 hours, but then you can see here that the protein starts to be produced. So this seemed to work in cultured cells. So now there's one thing that's important to remember. So I showed you this one example of this one mutation, but not all Duchenne patients have this mutation. There's over 8,000 different mutations described for Duchenne. So will this work for all patients? No, unfortunately not, because we know these crucial domains at the beginning and the end of the protein, they are crucial. So, I mean, we can restore the genetic code there, but it won't help, because if you don't have this domain at the beginning and you don't have the domain at the end, then the protein will not be functional. Well, fortunately, most patients have deletions in the middle of the gene. And that means that skipping certain exons applies to larger groups of patients. However, it's still all subsets. So skipping exon 51, the example that I showed, would apply to 14% of patients. So now we have a rare disease and we have a potential therapy that applies to a subset. So that makes things complicated. And you can see also that the applicability goes down quite rapidly. So then you have 45 only applies to 9%, and 43 would apply to only 3% of patients. So this does not apply to all patients, and skipping a certain exon only applies to a subset of patients. So that meant that we had to communicate this to the patient community. And we had to really explain to them how the approach worked, because they needed to understand. So before this approach was in development, it really did not matter that much what mutation patients had. So many parents were not really aware whether they had a deletion or whether they had another type of mutation, where the deletion was. So we needed to explain the approach so that they understood. And we needed to explain it so that they understood that this approach is not applicable to all patients. So we really had to do a lot of patient education, but also we had to set realistic expectations, because this is not a cure. What we're trying to do is to have Duchenne patients make Becker-like protein. And a Becker patient is still a patient. I mean, this is not, we're not curing them. We hope that this will slow down the disease progression. And then, of course, the question is this something that the patients want? I mean, and we can think that this is what patients want, but the only thing to find out is to ask. And this is again something that the American Patient Organization has done. They have asked caregivers, and they're now also asking patients, what they would want in a therapy and what side effects they would find tolerable to get a certain benefit. And the thing is that, so for instance, the Dutch Ethical Committee said, well, you don't need to do this. You know what the patients want. They just want to live longer. Well, actually, that was not the case at all. So longer survival was, I think, out of the 6 things, was at number 5. What patients wanted most was not to lose the next function. So the patients who were still walking wanted to keep walking, but the patients who were in a wheelchair, they wanted to be able to use their hand to feed themselves, the joystick, indeed the 6-minute PlayStation test. So this really showed that what they wanted most was not to lose the next function. So then something that slowed down disease progression, they all said, yes, this is something that we would like. But what also people said in advance, they will accept anything as long as there's a therapy. Well, this was also not the case, because they said, well, we're willing to accept certain risks, but maybe one risk, so risk for renal failure in 15 years. But if there was renal failure and cardiac problems and this, no, then they said, no, then it's not. So I think this really showed that, of course, patients, parents are very well able to balance these things, and they don't want a cure no matter what, and are not willing to take all risks, because this is, I mean, it's a deadly disease, but it's slowly progressive. So if you have a 4-year-old and you accept the risk that he will die in 1 year, I mean, the 4-year-old, he has a life expectancy of 25, 30 years. So this is not acceptable in this disease, and this was quite clear from this study. So then back to the therapeutic development. So we've seen this part, the cultured cells, which seem to work. But cultured cells are very easy. Because you have a small number of cells, you can just add whatever compound you have in high amounts. There's no circulation, so you don't need to think, well, will this be delivered to my tissue of interest? There's no immune system that can disable your therapy. There's no organs that can break down or clear your therapy. It's a first test, but it's easy. Then the next step is the mouse model. And for Duchenne, we have the MDX mouse. It doesn't make dystrophin. It's a naturally occurring mouse model. And so this, of course, this mouse does have organs. It does have an immune system, but there's still some limitations. And the first is that it regenerates very, very well. So that means that the muscle quality in this mouse is much better than in humans, or in Duchenne patients. So that means that if you have a therapy and you test it in this mouse, it will probably work a lot better than it will work in patients, because the muscle quality in the mouse is like 85-90%, while in patients it's maybe 25-30%. Another thing is that mice have very high metabolisms, and that means that things that are safe in mice may not be safe in humans, just because the mice break down the compounds, or break down toxins and clear toxins much more efficiently than humans do. So this is why in clinical trials, usually the first phase is a safety test, and only then, if the drug is safe, then you start testing also for efficacy. So we started thinking at the LUMC of clinical trials in 2005, 2006, and we started a collaboration with a company called Prosenza. And I think most people here in the audience know that we need companies to develop therapies. I mean, there are some examples of academically driven therapy development, but it's very expensive, and it's also the expertise that you need. We didn't have this at LUMC, so we needed a collaboration with the company. So that was quite helpful. So the first therapy we did was in 2006, local injection in 4 patients. So we skipped the healthy volunteer step. That is because for this approach, the skip of this exon restores the reading frame for Duchenne. But if you do this in a healthy volunteer, then it will disrupt the reading frame. Well, back then we said, well, maybe we make someone a Duchenne patient. Well, we know now we're nowhere near that efficient. But still, why would you test something in a healthy volunteer if the approach does the opposite of the therapy in a patient? So we tested in patients at first. So that meant we wanted to be really, really safe. So we did a local injection. So you see here anesthetic cream. You see here the injection. You see that the leg of the patient was fixed. So during the injection and during the biopsy, we fixed the food. And why did we do that? Well, we did a practice run in a rabbit because so this is the lower leg muscle. And what we knew, so the long back muscle of a rabbit is very similar in size. So let's do a practice run. And what we discovered during the practice run, because of course also there we marked where we injected. And then the next time, well, okay, so how exactly was the rabbit positioned when we did this test? Well, we didn't remember. And then, of course, the skin and the muscle moves independently. So then we said, okay, well, we think we did it like here, and then we took some biopsies from the rabbit, and then it turned out that sometimes we had the good location, but sometimes we didn't, just because the skin and the muscle, of course, moved independently. So that's why you say, okay, so we need to fix the foot to be able to find back exactly the location of the mutation. So a biopsy was done 4 weeks after the injection, and this is the healthy control DMD as a reference, and these were the 4 patients. So before the analysis was done, we had discussions like, when do we call this a success? Well, that was not really needed, because we saw very clearly dystrophin restored for each of these 4 patients. So that was great, but this is a local injection. You can't do local injections for 700 plus muscles, especially since the AONs don't have the eternal life, the transcripts don't have the eternal life, the protein doesn't have the eternal life, so you need to repeat this treatment like every week. So that means that, maybe one time you can talk a boy into getting 1 million injection, but if this has to be done every week, that's just not feasible. So we needed to work on systemic delivery. So we had done our clinical trial and then needed to go back to the mouse model. And I already mentioned that this mouse model is not perfect. Animal models are never perfect, but still you can use them to test certain things. So we used it to test the systemic delivery. And what we were told before we started doing this was the following. So we knew the AONs had been tested by other companies for cancer drugs mainly. And what we knew is that the uptake is mainly in liver and kidney and hardly in muscle. Well, we tested it anyway, and what we did, we tested it intravenously in wild-type mice, so unaffected mice, and in the MDX mouse. And then we checked the uptake in liver and 3 different muscles. Well, you can see in liver, indeed, there is a lot of uptake. And then, so this goes up to 12, and this goes up to 120. So, this is really a lot. Then, in the wild-type mice, indeed, we hardly found any of the AONs back in the muscles. But in the MDX mouse, we did. And at first, of course, we thought, well, someone made a mistake. They injected more in the MDX mouse than in the wild type. Turned out not to be the case. We repeated it several times, always got this. And then we thought, okay, so we know that the muscles of Duchenne patients are leaky because there's proteins leaking out. And actually this is step 1 of the diagnosis is to see where there's muscle damage proteins in the blood. If things can leak out, then maybe things can also go into the muscle. And so we speculate that because the muscle is leaky, the uptake of the compound in the dystrophic muscle is better than in healthy muscle. So actually the delivery is facilitated by the disease. So then we tested one other thing, and that is different delivery routes. So intravenous, subcutaneous, and intraperitoneal. And again checked in muscle, kidney, and liver how much of the AON ended up in the muscle, but also in the kidney and liver. And what you see, if you do intravenous, so into the bloodstream, the uptake by kidney and liver is quite high. If you do subcutaneous or intraperitoneal, the uptake in muscle is slightly lower, but the uptake in kidney and liver is much lower. So then we speculated, well, if you do subcutaneous delivery, that means there's less going to the tissues where you don't want the AON to go. There's slightly less going to muscle, but still there's good uptake. And also subcutaneous delivery is something that the patients can do at home. Well, intravenous delivery, you would need to go to hospital. And in a clinical trial setting, you would have to come to hospital anyway, but maybe afterwards, subcutaneous would be more patient-friendly, is what we thought, and hold that thought. So then we started thinking about efficacy trials. And only then we also started thinking of how drugs are approved. And for rare diseases, you all know this, drugs are approved by the European Medicines Agencies. And what do? They look at benefit risk analysis. And what you need to show is clinical benefit. And before, we were quite naive. So before we thought, well, we just need to show that dystrophin is back after we treat the patients. And then they will believe that, well, if the dystrophin is back, that will make the patients better. But of course, I mean, the patients don't care whether dystrophin is back. If they don't feel better, if there's no functional effect. So we needed tools. We needed outcome measures. We needed natural history. And we're now in 2008. And I show you this overview slide of the TreatMD neuromuscular network. And the aim of this EU-funded project, funded in 2007, was to make the neuromuscular field clinical trial ready. So all the things that you need for clinical trials, like biobank, patient registries, trial site registries, where do people see the patients, where are the expert centers, who has experience with doing clinical trials, so the outcome measures. So this network was initiated in 2007, and we wanted to do our clinical trials in 2008, 2009. So of course, by that time, we had a compound, but the field was not really clinical trial ready. The TreatMD network is still there, so since 2012, it's become the TreatMD Alliance. We're now global, so no longer EU only. But a lot of this work is still ongoing. So we're still not fully clinical trial ready, but we definitely were not clinical trial ready in 2008. Still, the trials were started. So several trials were started, and I will go over some of them. So we chose the subcutaneous delivery. We did a dose escalation study for safety, and then with the best dose, we did dose regimen, dose comparison, an efficacy, large efficacy study, and open label extensions for each of them. And we used as a primary endpoint the 6-minute walk test. In the 6-minute walk test, I mean, we did not have any outcome measure, and the 6-minute walk test had been used before by Pompeii, and was developed for the cardiovascular field. And what it is, you have two cones, 25 meters apart, and then you walk for 6 minutes as fast as you can, and then you measure how far patients can walk. And because Duchenne is a progressive disease, the idea was, when they go older, they will walk less far. And then imagine, I mean, this sounds really boring to us. Imagine you're a 6-year-old patient with a muscular dystrophy and you have to do this test. Still, we had nothing, and this was recommended by everyone. Well, this is the only thing that we more or less could use. So then all these trials were done, and in all of them, local injection sites were observed. So I mentioned it once, but imagine this was happening in all these trials. And we know now that this is a side effect of the subcutaneous delivery of our chemistry of AONs. When we made this decision of, well, this is more patient-friendly, we did not know this. In mice, we never saw any injection site reactions. We know now with intravenous delivery, there is no injection site reactions. So in retrospect, it was not a good decision. But of course, back then, when we had the information, we made an informed decision. But in retrospect, this was not good. In retrospect, intravenous delivery would have been better. There was also subclinical proteinuria seen in patients, and for some patients, thrombocytopenia was seen. But really, what bothered patients most were the injection site reactions.
Sorry, could you explain what those are?
So proteinuria means protein in the urine, and so that is a sign that there is maybe kidney damage or that the kidney is not functioning properly. But the thing is that even if you don't treat Duchenne patients, there sometimes will be proteinuria because there's a lot of muscle turnover. And well, at some point, I mean, the body can reabsorb only so much. Things got worse, so there was more proteinuria in treated patients than untreated patients, but when there was treatment breaks, it went away. So it didn't seem to be chronic or permanent, it seemed to be reversible. Thrombocytopenia means that there's less platelets in the blood, so that means that there's a risk of bleeding. This was seen in about 2-3 patients out of 300, so it was not common. It's also known for this chemistry of AON, and it's something that you can monitor. So when you see this, you can intervene, you can give the patient platelets, and you can stop the treatment. So the injection site reaction. So for some patients there was discoloration. You can see this here, and it's not that clear. And many patients had this, and some weren't bothered at all by it, but some were quite bothered by it. I said, well, I mean, if I go to gym, if I go swimming, everyone sees this, I don't like this. But some patients also had redness, induration. You can see here, a lot of the subcutaneous fat has gone away. And well, this really does not look good. And also, when you stop the treatment, this does not go away. So this was really felt by the patients and the parents that this was a problem. And this also meant that you can inject in different parts of the body, so you can rotate. But I mean, even after 12 weeks, this was not gone away. So that by the time they had to re-inject here, this became very painful. So it was clear that if you want to do this treatment, subcutaneous delivery is probably untenable, because I mean, this boy, I mean, you can't do the injection there anymore. And then of course you go to other sites, you get the same problem. So this was really the biggest problem that the patient had. So that were the side effects. Now on a functional level, so this is the 6-minute walk test of the first 12 patients who were in a dose escalation study. So they received a low dose, no side effects. They increased the dose in another cohort, no side effects. They increased the dose. And after 5 weeks of treatment, there were not really side effects. So they went with the highest dose, and then afterwards said to all patients, if you want, you can be in an extension study, receive weekly doses of the highest dose. And then they followed these patients with the 6-minute walk test. So 12 patients in the trial, only 10 patients in the slide, because 2 patients, by the time this open label study started, were non-ambulant. And if you're non-ambulant, you can't do the 6-minute walk test. Bear in mind, the majority of these 10 patients are non-ambulant. You see here the distance they were able to walk in 6 minutes. You see the 2 patients who walked least at the start of the study lost ambulation in about 1 year. The other 8 were more or less stable. So they received weekly injections for 1.5 years. So every week, go to the hospital, miss school, miss work for one of the parents, no holidays. And then they said, okay, well, this is very burdensome. Let's start changing the regimen. From now on, we will give you 8 weekly doses and then a 4-week off dose time, so that at least you have some time to rest. And we'll see what happens with the function. And actually the function did not seem to be affected. So here what you see is the patients seem to be stable for 3.5 years, which is not really what Duchenne is known for. With Duchenne you expect patients to get worse. So this was encouraging, but this is an open label study. So everyone knew they were being treated. So then there was a dose regimen study. And again, patients were followed with the 6-minute walk test, and this was done in young patients, so between 6 and 8 years old. The placebo group in blue, what you can see, over a year they lost about 30 meters. And now we know that this fits with the natural history. So if you follow patients in 1 year, they will at this age they will lose about 30 meters. Then you see in red the patients treated every other week with a double dose. And in green, the patients treated every week. And you see that these patients, again, seem to do better. There's a lot of variation between patients, small groups of patients, but the patients seem to do better. So then, of course, based on this data, people really anticipating the phase 3 trial. Oh, sorry, one more. Dose comparison. So again, in blue, the placebo, 3 milligram per kilogram, doesn't seem to be an effective dose. 6 milligram per kilogram. Again, so the dose used in the other studies as well, again, suggesting that the patients were doing better. So then people were really anticipating the large placebo-controlled trial. And the results were very disappointing. In blue, placebo, in green, the treated patients. And what you can see is that, the treated patients do slightly better, but it's only about 10 meters.
Finally, how was the treatment administered?
Subcutaneous. All of it subcutaneous. Yeah. Every week subcutaneous. And what you can see is that the treated patients do better, but it's not significant. And also it's not clinically relevant. I mean, if you're a patient, you don't care that you can walk 10 meters more in 6 minutes if you get these side effects. So what we know now, and we didn't know when we started, is that patients who are less than 7 are more or less stable. Patients who are over 7 years old, they progress. And what we had in our phase 3 clinical trials was a bunch of everything. So young patients who were stable, older patients who were progressing, regardless of the treatment. And then if you have a therapy that slows down disease progression, if patients are stable, you cannot measure a slower disease progression. If patients are really progressing quite rapidly, you're probably too late to intervene. So in retrospect, this trial setup was by no means ideal because we did not have information on the variation in the 6-minute walk test, the progression in the different age ranges. So there were power calculations done based on guesses. The cohort, the ideal cohort was not selected because what you want patients who are progressing slowly when you still can have a therapeutic effect, and not patients who are stable or are progressing very quickly. And I think, so if this therapy was a miracle cure, we would still have picked something up. But the problem was that if there was an effect, it was only minor. So what happens now? So Prosensa was by then acquired by GSK. GSK said, well, this is not working. We pull out. And then Prosensa was acquired by BioMarin, another company. What BioMarin did was they did a lot of retrospective analysis and then said, well, if we look in the patient group that we now think happy to redo this trial, we would choose this cohort. If we analyze just that cohort and all the patients that we've tested, we see an effect. And they applied with FDA for this, but the FDA said, well, we're not really convinced because you did a lot of extra analysis that you didn't plan on before, plus there are side effects. So we're not going to give you approval. They had one meeting with the CHMP behind closed doors, and a day later they withdrew their application. So, I mean, we weren't there, but we can all assume what this discussion was like. So then BioMarin said we stop the development of the exon 51 skipping compound, but also of other exon skipping compounds that had by then gone into clinical trials, because they said we will have the same problems with side effects, the same problems with limited efficacy. We will focus now on the next generation of AONs. So I will very briefly, because I know we're running out of time. So the 6-minute walk test was not designed by patients, with patients, for patients. But then the patient community, together with treating them, said we need better outcomes. And what they did, they started with the patients. And they asked in patients who were non-ambulant, what function do you find most important? And then they said functions that they found important, like, well, being able to feed yourself, scratch your nose, things like that. And then a test was made that tests in different ways whether these functions are maintained. So what this means is that if patients lose a point on this test, they have lost a function that we know is important to them. So this is a much better test, and also is, of course, a test that can be used in non-ambulant patients. Very briefly about trilateral education. If you want to read more, there is a paper about this. So what we've learned from our mistake is that we need to approach the regulators earlier. So with this new test, with other new initiatives that we have, we try to sit at the table with regulators, the academics, and the patients to really discuss, like, okay, so this is our perspective. How do you see it? And then everyone gives their perspective. And that means that rather than developing a test and then hearing when you have your test, well, actually it's not that good, you hear input from the beginning. And this works quite well. And we did this for DMD, and actually the spinal muscular atrophy SMA field has adapted the same approach, and they have organized a huge workshop with EMA as well in 2012. So I want to I know there's not a lot of time for discussion, but maybe for during lunch or during coffee breaks. So what we have now, we have another company in the US that has developed a similar drug to what we have developed. It has a lot less side effects, but it's not that effective. But they have pushed the FDA really to the brink, and in the end, FDA caved, and they have approved this not based on any functional test, but based on increases in dystrophin. And the problem that is existing now is that some patients have access to the drug because their health insurance reimburses it, but some patients do not because the health insurance says, yeah, but FDA says it's not functionally effective. They say this still needs to be proven. Why should we cover this very expensive drug? So it's a weekly intravenous infusion. So either patients get it and then it turns out that it is in fact not effective, and some FDA people say, well, this is just an expensive placebo, or patients do not get it and then it turns out that it is effective. So regardless, patients lose out. And I want to give this as a warning because I think you are a very educated crowd, and I don't think that you will want a therapy that's not effective. But this is just that because the company gave false hope, false expectations, the parents were so convinced that this was working, this was a cure, that they pushed death threats to FDA. They pushed, in the end, FDA approved it, and now we have a drug that we don't really know whether it's effective or not. And I don't think that that is a good situation. I think that what we want effective drugs, and not drugs where we don't know. So by 2021 they need to show functional effects, and well, let's hope that indeed they have functional effects, because the disease definitely deserves a treatment. I think that was all.
What was the delivery for that?
Intravenous infusion, so weekly.
Why the less side effects?
So no, also because they have a different chemistry. So they have a different chemistry, and that has less side effects. But the problem with that chemistry is that it's cleared very rapidly by the kidney. So they use very high doses, about 30 to 50 milligram per kilogram. Well, with our we used 6, so it makes it very expensive. And actually, the person who discovered this chemistry said the intravenous delivery with this chemistry is a very good way to make expensive urine. In half an hour, 99.9% is in the bladder. So they need these high doses to. And this is also why people wonder whether it's actually really working or whether it's just, yeah.
I wanted to ask, what exactly are the AONs, and how can you make sure that they're placed in the right position?
So,
how do you know that it's going to cover exactly that small piece?
So they're small pieces of modified RNA or DNA, and we know that DNA binds to each other. So the C always binds to a G, the T always binds to an A. So that way we can just design them. So if we want them to target exon 51, we pick a region in exon 51 that's not occurring anywhere else in the genome. So we're sure that they target only there and nowhere else.
So, okay. EON stands for, could you repeat it?
Antisense oligonucleotides. Yeah. So antisense because they target the RNA.
Just another question. You mentioned at some point that the quality of the mouse model is way higher, the muscle quality is way higher than in human. Would it be worth studying these aspects in order to help patients with Duchenne?
Yeah, so this is of course also something that has been done. But the thing is that mice are carrion eaters. They regenerate very well anyway. So this is just something that is inherent to the mouse. So if you do surgery on a mouse in the morning, in the evening you will only see a scar. So they just regenerate very well. And so it's not one thing, and it's also not specific to Duchenne. This is just inherent to the mouse.
So from the idea at the very start of looking at this might work, to the point obviously at the end where it was how many years?
So the work started in the late 90s, and the FDA approved the drug in 2016. And then you can still wonder whether, well, this drug is working or not. So it's been quite a while. And I think the thing is also that we did not want to wait for the outcome measures to be developed, because that takes another 5 years. But in the end, maybe that was not ideal, because you now have a drug where you think, well, maybe it works, but we just don't know because it wasn't properly tested. So I think the main lesson is that you don't only invest in research, but you also invest in tools to test whether your therapy is effective.
Well, I was just continuing really just on the mouse model. It's the first I'd heard actually about the mouse regenerating very quickly. And I'm just wondering if that applies to mouse models that are used in other, I'm thinking of the Rett syndrome mouse model actually.
So most mice will regenerate very well. And so not just for muscle, just for every. And another thing is that these mice are inbred strains. Yeah. And the genetic backgrounds can really make a lot of difference. So some backgrounds regenerate less well than others. So now, of course, what we're trying to do is have this mouse on a background that regenerates less well, so that it looks more like the Duchenne patient.
Yeah, that's very interesting.
Yeah. Okay.
Okay, thank you very much.
Thank you.